Hey folks, I'm back again. Hopefully you're not bored of me. So I was asked to give a progress report on decentralized AI. I'm not sure what the level of the audience is, so I've tried to keep this like middle of the road level, but I don't know, maybe somehow signal to me if it goes too deep or too high level, and I'll try and bring it a different way. But I'm probably going to have to go through this quite quickly. I think I have 15 minutes and a few more than 15 slides. So I'll jump straight into things. And if we have time at the end, I'll happily answer questions. So very quickly, background on me. Why would you listen to me and what I say about this? So very quickly and briefly, I'm Ben, a co-founder and CEO of Jensen. My background is in machine learning research. So I did my doctorate in deep learning, specifically on the application of evolutionary algorithms to the optimization of the structure of deep neural networks. And so deep neural networks are the networks that we use for most machine learning tasks nowadays. LLMs are an example of a deep neural network. CNNs are an example of a deep neural network used in the computer vision space, which is where my research was. All of these networks are essentially huge graphs. They're graphs of layers of matrix multiplications, essentially. And you just do loads and loads of matrix multiplications. You multiply numbers together. Out of the end of that, you get intelligence, theoretically. Those graphs have a particular structure. And my research was in optimizing that structure. So taking those layers of matrices and putting them together in different orders and things like that. Back in the day, back when machine learning was kind of kicking off in anger in like the early 20-teens, this was done by hand, by people. So people would sit down and they would figure out what that graph should look like. Basically, they would stack all of these matrices together in a certain order. They would name it after themselves, and then they would publish it at a conference. And all of the other researchers would then use these named models. At the time, people got pretty bored of that. It wasn't very interesting, and so we applied automated methods. And that was my research, using automated methods to do that instead of getting people to do it by hand. Since then, I've co-founded my previous startup in data privacy, and 5.5 years ago, I co-founded Jensen and basically discovered decentralization as a kind of technique. Before that, I was in the centralized machine learning world totally in research. So that's a bit about me. I'm going to move on. I'm going to go through some basics. I'll do this pretty quickly. And then we're going to go into what has happened in decentralized AI. So basics, what is machine learning? What I want to do here with this slide is just communicate that it's not just language models. It's not just ChatGPT. It is, in my opinion, a set of techniques for compressing raw kind of analog data that exists in the world into a new representation. That new representation is the weights of a machine learning model. The weights are all of those matrices of numbers that exist within the model. They're the kind of gigabytes of data that hold the intelligence of that model. And what you're essentially doing is taking enormous amounts of raw data that exists in the world, some kind of truth signal. So that could be somebody labeling that data. I could take a picture of this room and I could say it's a conference. And then I could train a machine learning model on loads of those images, and it would start to learn what a conference looks like, basically. So that's supervised learning. You can do that on any type of data, theoretically. And so LLMs do this autoregressive language prediction task, but there are many other things that you can do. And what I've tried to communicate up here is they're just one class of model. We use lots of different classes of model. They are exciting right now because they sort of encompass foundational knowledge from language, but there are many other techniques. And at Jensen, we believe quite strongly in that pure kind of underneath compression mechanism that's applied to anything, not just language models. So I just wanted to kind of make that clear. Obviously, use cases are probably infinite. So I touched a little bit on this with supervised learning, the idea of taking labeled data and processing it through models to get them to learn a concept from the data. There are also many other techniques to train a model. And so doing that process of taking that raw data and compressing it into model parameter space can be done with many different targets. Supervised learning essentially minimizes the distance of the output of a prediction of a model. So it says, if we say, is this room a conference? 1 means yes, 0 means no. The model might output 0.7. The difference between that 0.7 and a 1 is how wrong the model is. And we just use that signal of how wrong it is to train the model. And that's a very simple explanation of supervised learning. But you can create many, many, many different ways of giving it a signal about how wrong or right it is. And all of these ways up here are used in different use cases. Most recently, most foundation models or most LLMs that you see being trained use a technique called reinforcement learning, which happens after you've done that supervised learning stage. And so the world will talk a lot about reinforcement learning. You've probably seen loads of stuff about it recently. That is just one technique for aligning models behind some kind of signal, but usually all of these techniques are used at some portion of the model's creation. So moving on, we have this process of taking all of these weights, these matrices. We have a process of telling them how wrong or right they are, getting them to update their priors, essentially, and that is the training process. But what does that actually involve? Like, what does it require? And so it requires, in our opinion, 4 specific things. And if anyone's read our light paper, which we wrote back in 2021, we said 3 things back then. I've added a 4th thing here, which is truth, that I'll get onto in a minute. But essentially, the main things that you need are compute. And so when you're training a model, you're updating these parameters. You're doing all of these matrix multiplications. Those things have to be processed. These are just mathematical operations. That requires a compute device of some kind, a CPU, a GPU, a TPU, a parallel processor, something like that, to do enormous amounts of mathematical operations. It turns out training a machine learning model requires an absolutely ludicrous amount of mathematical operations, which means compute was, earlier in this kind of cycle, the bottleneck for machine learning. It was the thing we needed to scale to make models good. In my opinion now, it's actually no longer the bottleneck, but it is a bottleneck. You still need access to enormous amounts of compute to train models. Next up, you've got data. So if I wanted to train a model to detect whether or not something is a conference from images, I'm going to need loads of images of conferences. Like, that's just how I'm going to give the model some kind of information about what a conference is. That's pretty self-explanatory, but it applies beyond images. It applies to absolutely everything. And so that's the idea of raw data. Every sensor in the world is generating raw data of some kind. It's taking the analog kind of structure of the world and it's putting it into the digital space. If you take an image, that's what you're doing. If you take an audio recording, that's what you're doing. All of these things create data that is then used to train models. Next up, you've got human entropy. This is essentially signal. And so in the supervised learning era, this was the idea of labeling a bunch of data. And so Scale AI came along and said, hey, we can just pay loads of people to do loads of labeling effort, and we solve that human entropy problem for the world. And so they kind of alleviated that bottleneck and became a $14 billion company from doing that. In my opinion, that isn't actually scalable. That's a proxy approach of scaling human entropy. In reality, human entropy comes from every interaction you guys have with technology. Every click you do on your phone, every click you do on your computer is actually human entropy information that could train a model. And so actually, realistically, we probably want to capture that. But we need it for training models. Finally, I've added truth here. Truth takes the place of human entropy when you scale beyond humans. And you say, actually, what are we getting from the humans? We're getting some signal of truth. Who's to say that this room is a conference? We decide that humans labeling images is the way that we say it's a conference. But actually, in the post-human era, we might decide that completely differently. And we, right now, assign truth to humans via the consensus that I talked about on the last panel. And so the academic peer review process, et cetera, is just lots of people agreeing that something is true. We'll actually want to extend that to machine learning models in the future. As they start to become intelligences somewhat equivalent with us, we'll want them to have a space in the arena to decide what is and isn't true. And so actually, in a way, I think that human entropy portion is going to fade away. And actually, truth is going to be the third and final requirement that we have for machine learning. But that's for another day. I need to get on to decentralized AI. So heading towards decentralization. Solving those problems that I talked about before at scale is very hard to do. And so the machine learning world started out just training a single model on a single GPU with a bunch of data that was labeled by a small group over maybe a day or a few days or a week or something like that. Very quickly, it became clear that that wasn't enough, and we actually needed to use more resources. So we needed to access more compute, more data, more human entropy, etc. And so what happened from that was the idea of distributed techniques. And so this is training a machine learning model using more resources than you could have otherwise done in a singular case. From that, we have 4 essential ways of doing distributed training of machine learning models. And I'm skipping through this very rapidly. Please Google things or talk to me after if you want more information on it. But basically, these 4 methods are data parallel, the idea of saying we need huge amounts of compute to train this model. We've got loads of data. How do we get it into the model in the most efficient way possible? Data parallel says just make a bunch of copies of the model and train all of them at the same time on different pieces of data and then combine them. And in doing that, you've accessed way more compute to train your model on the same amount of data. So you've just copied the model a bunch of times. It allows you to train essentially 2 samples into the model at the same time as you could have otherwise only trained 1. If you scale that across 1,000 devices, you're training 1,000 examples into the model at the time you would have previously scaled 1 example in. So this allows you to, using enormous amounts of compute, speed up your model training. But that's kind of all it does. Next up, you've got pipeline parallelism. This allows you to make bigger models. And so this is saying, I have a model, which is a graph, as I mentioned before. That graph is a series of layers that get executed, a series of matrix multiplications. It needs to fit in memory on a device. And so if I have a 16 gigabyte GPU, I can only fit not even a 16 gigabyte model. I can only fit a model smaller than 16 gigabytes. If, however, I split that model in half, put the first half on one GPU and the second half on another GPU, and just get them to communicate what happened in between themselves, then I can make a bigger model. And so pipeline parallel allows us to make bigger models by using more compute, but there has to be communication between the devices. Next up, you've got tensor parallel. This is a bit more complicated, but says instead of splitting the model kind of vertically and taking the first half, putting it somewhere, second half, putting it somewhere else, actually split it horizontally and say, I'm going to do a portion of this data sample on one device and a portion on another device. In that way, I can split the model in a horizontal way over multiple devices, but again, wild communication required between those devices. Finally, you've got expert parallelism. This gets into a mixture of expert style models and the way that transformers are designed with expert layers and expert heads. You can split those up as individual models in their own right and say, actually, my model is made up of many tiny models, and those tiny models can all exist as individuals over different devices. If you look at this and say, well, can we combine all of those things? Then yes, you're absolutely right. And that's what happens in practice. And so right now, people will use FSDP2, Zero, or the DeepSpeed framework, Megatron, etc., to do all of this process automatically for them when training a model. But essentially, you're taking all of those computations and you're splitting that graph over many different devices in order to be the most efficient it can possibly be. Problems with this typically relate to communication efficiency. You need to be able to communicate information between all of those devices as fast as possible, which is why you see Meta, DeepMind, OpenAI, etc., build these massive data centers and stuff GPUs into them, because you need to be able to communicate between those GPUs incredibly rapidly. With decentralization, we can access enormous amounts of compute across the world, but we have a communication problem, which I'll go on to the kind of solutions that we've seen to that as we go. So I talked about distribution there. Crucially, that was distributed training. It wasn't decentralized training. What I really care about is decentralized training. And so the distinction I will give to you with decentralized training versus distributed training is that in distributed training, that coordination of what's happening can happen in a centralized way, i.e. one person somewhere or one device is deciding what happens when you split models up in all of these weird and wonderful ways. You send data samples all over the place. You send experts all over the place. Someone or some entity is in the middle deciding where those things go. It turns out making that decentralized is actually pretty difficult, but has huge scaling benefits. The biggest problem you get if you say, I want to decentralize this rather than distribute it, is you start to have trust issues. Because at that point, you don't know necessarily who is participating. In the distributed world, you have a centralized point of authority, which can KYC everybody. It can kick out people who it knows are misbehaving. It can verify people, etc. In a decentralized context, you're going to need to make decisions via the decentralized nodes. You're going to have consensus mechanisms. You're going to have decision made by the crowd, etc. Then you get the Byzantine generals problem. And so we need to solve that somehow. TLDR, we can solve that with crypto rails, which is the most exciting kind of combination of decentralization and model training, in our opinion. Up here, I've got the progression that's happened with distribution into decentralization. You start out with parameter server training of machine learning models. This is the idea that in a data parallel context, if we're training the same model over 1,000 nodes with different data, we can get them all to send their models to one place. We average them together, and then we have one model that's taken the information from all of those models. Nice and easy, very centralized. You can move that on to a slightly less centralized case by doing an all reduce, which is an operation that happens collectively across nodes, where they all essentially combine their knowledge together. You can then take that even further to decentralization by doing that over gossip networks. So the DHTs that underpin all crypto networks can be used for communication in a completely fault-tolerant way. And I realize I am skipping very rapidly through this. So any kind of questions on this, again, send them to me offline or read the stuff that we've put out as Jensen, because it should communicate a bit more about this. Okay, moving on. So the progression, this is what this talk is supposed to be about. I'm going to move through this quickly because there's a kind of long history here. So in the early days, pre-2012, we had neural networks going back to the 40s. This isn't a new thing. What is new is that deep learning came about in the early 2000s, and then very particularly in 2012, we started 2011 technically, if you believe certain researchers in the space, but we started accelerating machine learning models with GPUs, and that's when things actually got really exciting and came out of pure kind of mathematical theory and became something that we could do in practice in the real world. After that, there was an explosion of compute usage. And so we realized, actually, we've accelerated on this single parallelized device. Let's start accelerating even more and even more and even more. There was a bunch of infrastructure released, which allowed researchers to do this. And very importantly, I started my PhD in 2015 and kind of came into this space. TPUs are on here as well as an interesting first foray into parallelized devices that weren't GPUs. They weren't general purpose. They were specifically for machine learning. You've probably heard a lot about other tensor processing units since then. So that was the acceleration phase. That was saying, okay, mathematical technique, it's now usable in the real world because of compute. Next up, we started moving beyond single device. So we started building clusters, we started doing distributed learning, we started accelerating machine learning training across many GPUs. This was mostly happening in research labs and in big tech companies like Google, etc. For the average researcher, so for me at the time while I was doing my research, I couldn't access clusters. They just weren't available to me. I could access maybe 4 GPUs on a single device, which is how I did my research, but that was the extent of my distributed training ability, essentially. And so right then and there, it was very clear that compute was the bottleneck because only very large companies could actually accelerate these models. Towards the end of that period, getting into 2020, there started being forays into answering the question, what if we did this over consumer devices in a collaborative way instead of on clusters? And so this took inspiration from things like SETI at home, Folding at home, which sort of came afterwards, Boink from Berkeley, which was a parallel processing system for allowing people at home to run these operations that would help progress science. And from that came HiveMind or Learning at Home and a system called Deadlock, which was the ability to train machine learning models, not over a cluster in a data center, but actually over people's devices at home. It was incredibly slow. It was very, very nascent, but it worked and it showed some degree of training performance. And so this was the first time we moved into the kind of commodity consumer device resource system for training machine learning, getting towards decentralization. Next up, we got distribution. So we started moving away from these single clusters and into multiple clusters. And so big tech started waking up to the need to go beyond a single data center. We got Pathways from Google. We got Palm, which is Google's enormous language model. We had open source models being created by people other than the big tech companies. And crucially, a paper called Diloco out of Google Research, which showed that you could do very low communication distributed training. The intention of this was to basically link 2 data centers together instead of just using one. It was a very kind of simple way of saying we can have islands of compute and we can train machine learning models over those islands of compute. Oh, my time's up. I'm going to have to move very quickly. But it showed that it was possible, and it showed that big tech was waking up. In the decentralized world, we were exploring much more open techniques, but we'll go into those as we go. So next up, in 2025, and I guess moving beyond, we start to explore different model architectures. So mixture of experts models, that expert parallelism I mentioned earlier. We move into accessing data that exists at the edge. So instead of just saying, let's distribute the compute because compute is the bottleneck, we go beyond that and we say, actually, data is now the bottleneck. The reason you're not seeing vastly different models out of big tech right now is because they've saturated the existing data that they have. They have a problem now, which is high quality data. And our intuition is you can solve that with decentralized and distributed training, but it requires entirely new methods. And so this is where I think decentralized AI gets really interesting. What you'll notice from the way I'm speaking, though, is I don't think compute is the problem that decentralized AI should really solve now. It was the problem, but that problem got solved by centralized methods in a big way. The cost of compute came way down. Access to compute went way up. We got many more chips, and so it's not that big a problem anymore. But data is a problem. And so if you take anything away from this, take away the fact that I think decentralized AI will have its biggest effect from sourcing data from everyone rather than sourcing compute. I'm going to move very quickly. Okay, decentralization. You guys all get decentralization. I'm not going to talk about that. We've talked about decision making and prediction markets. You can look at what it means from a crypto perspective. So where are we now? Now, I think we have pre-training runs that run in a decentralized way. In my opinion, they're proof of concept. They have little differentiation from centralized methods. They have not been particularly interesting. On the post-training side, we have embarrassingly parallel rollout generation. This is reinforcement learning on top of models. This is very interesting. We are seeing some benefits from reinforcement learning, but again, it's proof of concept. On the execution side, compute networks, bringing down the compute cost by using decentralized compute. As I said before, I think there was a point in time where this was very important. In my opinion, this point in time has largely gone. Centralized networks, centralized compute is actually very cheap now. I think when we scale up compute to happen locally on all of your devices, then decentralized compute networks make sense. But as a pure compute resource network, kind of makes little sense. Okay. I'm not going to touch on agents. You've heard enough about agents. What's next? Productization. So I think what we really need is decentralized networks and protocols to prove that actually we can build products on top of this stuff. Not try and build a new compute network, not try and build a new AWS, build a real product which benefits from decentralization. They're going to pull me off the stage in a minute, so I'm going to wrap up very quickly. Okay, final 3 points. 3 things required for machine learning to become decentralized. You need signal. This is that human data. It's the data from all of your devices. You need to get that from human action. That happens locally on your devices. Decentralized networks need to access that. Scale. You do need to horizontally scale compute, but not by booking compute time on other people's devices, by doing it within the applications on your devices as and when you interact with them. And finally, eval. We need some proof that these models are any good. In my opinion, we solve that with a form of prediction market that I mentioned on the previous panel. If you have any questions on any of this, please follow up with me because I've taken way too long. But thank you for listening, and you can find me on Twitter, anywhere, email, etc.